Welcome back. Today, we transition from theoretical quantum mechanics to high-temperature materials engineering. We are analyzing the Czochralski, or CZ, growth method, the foundational metallurgical process responsible for over 90% of the world's monocrystalline silicon. If you are holding a smartphone, a laptop, or looking at a server rack, every single logic gate and memory cell inside those systems traces its lineage back to a Czochralski furnace. The origin of this technique is a masterclass in serendipity. In 1916, Polish metallurgist Jan Czochralski accidentally dipped his pen not into his inkwell, but into a crucible of molten tin. As he pulled the pen out, he noticed a continuous, thin filament of solidified metal trailing behind it. He discovered that this filament was a flawless single crystal. While the fundamental concept of pulling a crystal from a melt hasn't changed, scaling this up to semiconductor-grade silicon required overcoming a massive barrier: structural defects. In its infancy, thermal shock would rip dislocations through the crystal lattice, rendering it useless. This bottleneck persisted until the 1950s, when William Dash introduced a revolutionary necking technique to filter out these defects. To understand how Dash's technique works, we first have to understand the foundational thermodynamics that govern the boundary where liquid becomes solid.
At its core, the Czochralski process is a meticulously controlled first-order thermodynamic phase transition. We are transitionary biasing a system from a disordered liquid phase to a highly ordered solid crystalline lattice. For silicon, this phase boundary is locked at its melting point of exactly 1,417 degrees Celsius. To maintain a stable crystal growth rate, we must control the thermal equilibrium at the solid-liquid interface. The governing steady-state heat balance equation can be expressed as shown on the screen, where K sub S and K sub L are the thermal conductivities of the solid and liquid phases. dT by dx represents the respective temperature gradients, L is the latent heat of fusion, and V is the pull velocity. Every joule of latent heat released as silicon crystallizes must be efficiently conducted up through the growing crystal ingot and radiated away into the water-cooled walls of the vacuum chamber. If the pull speed V is too high, the latent heat builds up, localized remelting occurs, and the single crystal structure collapses. To execute this delicate thermodynamic balance in the real world, the process follows a strict, highly sequential engineering phase, beginning long before a single crystal even begins to form.
Number 1. Crucible charging and meltdown. That real-world execution begins with crucible charging. The raw material is electronic-grade silicon, or EGS, an ultra-pure polysilicon with impurity levels below 1 part per billion. This material is loaded into a high-purity silica, or SiO2 crucible within a cleanroom environment. Because silica is highly brittle and susceptible to thermal shock, structural packing is critical. Technicians place smaller silicon particles at the bottom to act as a protective cushion, shielding the quartz from being gouged or cracked when the larger, heavier silicon chunks settle during meltdown. Once charged, the system is sealed and evacuated. We introduce a continuous, low-pressure flow of highly pure argon gas to protect the system. At 1500 degrees Celsius, molten silicon is aggressively reactive. It will readily oxidize or react with nitrogen, meaning any ambient atmospheric gases would catastrophically ruin the batch. The crucible is heated via radiofrequency or resistance heating elements to just above the melting point. This meltdown phase takes anywhere from 2 to 10 hours. The thermal margin here is incredibly tight. Overshoot the temperature by too much, and the structural integrity of the silica crucible itself will fail, causing it to collapse under its own weight.
2. Seeding and crystallographic orientation. Once the molten silicon is completely liquefied and thermally stabilized, we introduce the structural blueprint, the seed crystal. This is a small, structurally perfect rod of monocrystalline silicon, pre-oriented along a specific crystallographic axis, typically 100 or 111, depending on the desired electronic properties of the final wafers. The seed is lowered until it just touches the surface of the melt. It is held there momentarily to undergo thermal equilibration, bringing its temperature right up to its melting threshold without causing it to dissolve.
This seed acts as a macroscopic template.
The uncoordinated, chaotic atoms of the molten silicon bump against the highly ordered lattice planes of the seed, instantly aligning themselves to mirror its exact atomic orientation, plane by plane. However, the moment this cold seed touches the white-hot melt, a massive engineering problem arises: thermal shock. 3. The dash necking technique, eliminating dislocations. This thermal shock inevitably introduces line defects known as slip dislocations. If these dislocations propagate into the main body of the crystal, the resulting ingot will be structurally useless. This is where William Dash's necking technique comes into play. To eliminate these defects, the initial pull speed is accelerated drastically. This rapidly narrows the crystal diameter down to a mere few millimeters, forming a long, thin neck. The underlying physics of this process is elegant. Dislocations prefer to propagate along specific close-packed crystallographic directions, in the case of silicon, the 110 direction. By intentionally growing the crystal along a different orientation, like 100, and forcing a rapid, narrow vertical growth rate that exceeds the climbing rate of the dislocations, these line defects are literally forced to grow outwards to the physical boundary of the neck. They run out of material, terminate at the surface, and leave the core crystal matrix completely dislocation-free.
4. Crown and body growth phase. Once the dislocations are filtered out and left behind in the neck, we can safely grow the usable portion of our crystal. The pull speed is reduced, and the temperature is subtly lowered to initiate the crown. This allows the crystal diameter to expand outward until it reaches its target production size, typically 200 millimeters or 300 millimeters in diameter. Once the target diameter is established, we enter the steady-state body growth phase. To maintain a constant diameter throughout this long cylinder, an automated control loop constantly balances the thermal environment by modulating pull speed and heater power. But maintaining a constant diameter is only half the battle. We must also ensure chemical homogeneity. To achieve this, the crystal holder and the crucible are rotated in opposite directions. This counter-rotation is essential for fluid dynamics. It drives forced convection currents within the molten silicon, minimizing thermal asymmetry across the melt and ensuring a highly uniform distribution of dopant atoms. Eventually, as the molten raw material is depleted, the growth run must come to an end, bringing us to the final step of the physical growth cycle. 5. Tail formation and thermal shock mitigation. We cannot simply yank the finished crystal ingot out of the melt when the body is complete. Doing so would subject the white-hot solid to a sudden, catastrophic thermal shock as it hit the cooler ambient gas, propagating destructive slip dislocations all the way back up into the pristine body we just grew. To prevent this, the temperature is slowly raised while the pull rate is adjusted to gradually taper the diameter down into a sharp cone, or tail. This slow reduction in contact area gracefully decouples the ingot from the liquid melt, preserving the structural perfection of the usable silicon body above it. With the physical structure of the ingot successfully secured, we must now pivot to look inside the lattice itself, where subtle chemical interactions during growth dictate the wafer's ultimate electrical behavior. Section 4. Material properties and impurity management. Controlling the geometric shape of the ingot is meaningless if we do not also control its electrical properties via dopant control. A precise mass of dopant material, such as boron for p-type or phosphorus for n-type semiconductors, is added directly to the crucible charge. However, managing dopant concentration throughout the length of the ingot is complicated by a thermodynamic phenomenon known as segregation. The equilibrium segregation coefficient, K0, is defined as shown on the screen, where Cs is the concentration of the dopant in the solid crystal, and Cl is its concentration in the liquid melt. For most dopants in silicon, K0 is less than 1. This means that as the crystal solidifies, it preferentially rejects the dopant atoms back into the liquid melt. Consequently, the melt becomes increasingly concentrated with dopants as the run progresses, causing the tail end of the ingot to be more heavily doped than the seed end. Furthermore, we must account for unintended impurities.
Because molten silicon is in direct contact with a quartz SiO2 crucible, a minute amount of the wall dissolves. This introduces interstitial oxygen and carbon into the silicon matrix. While excessive oxygen can cause unwanted thermal donors, controlled amounts are actually highly beneficial. They act as structural pinning centers that mechanically strengthen the silicon wafers and enable internal gettering, a process where oxygen precipitates trap unwanted metallic impurities away from the active device regions on the wafer surface.
To summarize, the Czochralski process is a magnificent synthesis of thermodynamics, fluid dynamics, and crystallography. By transforming raw, disordered polycrystalline silicon into a massive, dislocation-free, single-crystal macroscopic lattice, the CZ method bridges the gap between raw earth and the atomic-scale substrate required for modern microelectronics. Let's review the critical engineering milestones we analyzed today. The core thermodynamics, maintaining a strict phase transition boundary at 1417 Celsius by balancing latent heat dissipation with pole speed. The dash necking technique, accelerating early growth to force thermal dislocations to propagate outward, leaving a perfect single crystal core. Rotational kinematics, using counter-rotation between the seed and crucible to control fluid convection, stabilizing both temperature and dopant mixing. Chemical segregation, accounting for the K0 segregation coefficient as dopants are rejected into the melt during growth. In our next lecture, we will examine the mechanical and chemical processes used to slice, lap, and polish these giant ingots into the ultra-flat, mirror-finished wafers that enter the photolithography tracks. See you then.